Our planet's safety is a dangerous illusion, a fear that echoes the stark warnings of figures like the late great Stephen Hawking. A new bombshell report reveals a terrifying truth. A nearby passing star could easily fling Earth from its life-sustaining orbit. This shocking threat is based on stark new scientific simulations. Are we just living on borrowed time, awaiting a cosmic sledgehammer? For generations, we have been comforted by the model of a stable, predictable solar system. We learn of the planets held in their stately, near-circular orbits by the sun's immense gravity, a system that has persisted for more than 4.5 billion years, allowing life to arise and flourish on at least one of its worlds. But you won't believe what just came out. A groundbreaking paper by astronomers Nathan Kaib of the Planetary Science Institute and Sean Raymond of the University of Bordeaux has delivered a terrifying reality check to this cozy picture. Their work, detailed in a paper submitted to the astrophysical journal Letters in early 2024, suggests that our planetary home is not an isolated, protected system. Instead, it is a participant in a chaotic, galaxy-sized game of pinball, and an outside force could violently tilt the board at any moment. This is a paradigm shift in how we understand our long-term security. The threat isn't necessarily a direct impact from a rogue asteroid, a danger that agencies like NASA are actively working to mitigate through programs like the DART mission. This is an entirely different class of catastrophe, more subtle in its origin but infinitely more devastating in its conclusion. The new research demonstrates that a celestial intruder, a star just passing by in the night, doesn't need to come anywhere near Earth to sign our death warrant. By delivering a slight gravitational nudge to the outer edges of our solar system, it can set in motion a chain reaction of chaos that could take millions of years to unfold, but which ends with the utter annihilation of our world. Are we, and our celestial neighbors, just pins in a cosmic bowling alley, waiting for a stray star to score a strike? The thing is, to understand this newly quantified threat, we must first abandon the notion of space as a static, empty void. Our solar system is not a fixed display in a quiet museum. It is a dynamic entity, hurtling through the Milky Way galaxy at a staggering 515,000 miles per hour. As we travel, we move through a diffuse sea of other stars. While space is indeed vast, it is not empty. Stellar flybys, moments when another star passes relatively close to our own, are not a matter of if, but when. Astronomers have long known about this reality. It's estimated that a star passes within the bounds of the Oort cloud, a theoretical, immense sphere of icy bodies surrounding our solar system, extending out nearly 2 light-years roughly once every million years. A much closer pass, within 10,000 astronomical units, where 1 unit is the distance from the Earth to the Sun, happens on average every 20 million years. For decades, the primary concern with these stellar flybys was their potential to disrupt the Oort cloud, dislodging comets from their stable, distant orbits and sending them plunging toward the inner solar system, raising the risk of a catastrophic impact. This is a serious threat in its own right, the likely cause of past mass extinctions on Earth. This isn't just the stuff of scientific papers. It's a fear that kept the world's greatest minds up at night. The renowned physicist Stephen Hawking, never one to shy away from uncomfortable truths, often spoke with grave concern about this very scenario. He warned that the solar system is a cosmic shooting gallery and that a random asteroid impact is not a question of if, but when. For Hawking, the nonchalance with which humanity treats this existential risk was baffling. He viewed a catastrophic impact as an inevitability on astronomical timescales, a ticking clock against which our species' only long-term hope was to become multi-planetary. But the research from Kaib and Raymond elevates this threat to an entirely new existential level. The danger isn't just about a few incoming snowballs, however large and destructive they may be. The true, terrifying risk is that the gravitational pull of a passing star can fundamentally destabilize the very architecture of our solar system itself. The gentle gravitational tug from a star that we would never even see with the naked eye could be the first domino to fall in a sequence that ends with planets crashing into one another. The new simulations show, for the first time with terrifying clarity, that the stability we take for granted is conditional, and the conditions can be changed by a random passerby. So, how did they figure this all out? You see, behind the scenes, what Kaib and Raymond did to arrive at this horrifying conclusion wasn't about looking through a telescope and spotting an incoming stellar menace. They did something far more comprehensive. They ran thousands upon thousands of sophisticated N-body simulations, powerful computer models that calculate the gravitational effects of multiple objects on one another over vast stretches of time. These simulations are the modern astronomer's crystal ball, allowing them to play out the future of the solar system under different conditions. For decades, these long-term simulations, like the groundbreaking work of French astronomer Jacques Lascar, focused on the internal stability of the solar system as an isolated system. These models already revealed a small but non-zero chance of chaos, finding a roughly 1% probability that Mercury's orbit could become dangerously unstable within the next 5 billion years due to a gravitational resonance with Jupiter. This instability could cause Mercury to be ejected from the solar system, crash into the Sun, or collide with Venus or Earth. What Kaib and Raymond did was introduce a crucial, previously underaccounted-for variable into this already fragile equation: the external gravitational influence of passing stars. They programmed their simulations to include the effects of stellar flybys at various distances and masses, reflecting the real environment our solar system travels through. They were no longer modeling a pristine, theoretical solar system in a vacuum. They were modeling our solar system as it actually exists in a dynamic, sometimes crowded, galactic neighborhood. The results of adding this single touch of realism were nothing short of apocalyptic. And the results that emerged from the humming supercomputers? You won't believe how stark they were. The simulations confirmed that the greatest threat is not a direct gravitational pull on Earth. The true danger lies in the subtle, insidious influence these passing stars exert on the gas giants at the edge of our solar system, particularly Neptune and Uranus. A stellar flyby can impart a tiny gravitational kick to these distant worlds, slightly altering their vast orbits. On a human timescale, the change would be imperceptible, but over the course of millions of years, this tiny deviation acts like a poison, slowly propagating inward through the solar system's gravitational web. This is the domino effect from hell. The change in Neptune's orbit ever so slightly alters Uranus's, which in turn alters Saturn's, which then alters Jupiter's. Once the orbit of Jupiter, the 800-pound gorilla of our solar system, with more than twice the mass of all other planets combined, is significantly perturbed, all bets are off for the small, rocky worlds of the inner solar system. The delicate balance that keeps Earth, Venus, Mars, and Mercury in their safe orbits is shattered. The numbers, while small in percentage terms, are existentially terrifying in their implications. Kaib and Raymond simulations found that the overall risk of Earth being catastrophically affected, either thrown into the Sun, ejected into the freezing void of deep space, or forced into a collision with Mars or Venus, was a chilling 0.2% over the next billion years. For Mars, the chance of being lost was 0.3%. While these numbers sound low, they represent a dramatic increase over the odds in an isolated system. More importantly, when the consequence of that tiny percentage is the complete and utter end of human civilization and all life on Earth, any probability greater than zero is a cause for profound alarm. One roll of the cosmic dice out of 500 could spell doom. Over the immense timescale of 1 billion years, the galaxy gets many, many rolls of the dice. But it's really strange, because the rabbit hole goes deeper. Perhaps the most bone-chilling aspect to emerge from the research is a small but devastating sentence in the paper's abstract. Instabilities induced by stellar flybys are much more likely to involve the loss of multiple planets. This is a crucial distinction that elevates the scenario from a planetary threat to a systemic collapse. Previous models of internal instability often resulted in the loss of a single planet, most commonly Mercury. But the chaos triggered by an external stellar kick is far more violent and widespread. The simulations by Kaib and Raymond showed that once the gravitational chain reaction begins, it doesn't just neatly pluck one planet out of the system. It can lead to a complete and utter meltdown of the orbital architecture. Imagine a scenario where a destabilized Mercury careens inward toward the Sun, while a perturbed Mars is sent hurtling outward. Earth could find itself caught in a gravitational crossfire, its orbit torqued and twisted until it is sent on a collision course with a panicked-looking Venus. The very fabric of our solar system would unravel. It wouldn't be the loss of Earth. It would be the destruction of the solar system as we have known it. A planetary demolition derby on a scale that defies human imagination. The stability we see today is not a guarantee for tomorrow, and the new research shows that when things go bad, they go catastrophically, system-wide bad. Now, what really brings up a lot of questions is the official response. In the face of research that outlines a credible, albeit long-term mechanism for the complete destruction of our planet, one might expect an immediate and robust response from the world's leading space agency. What has been the reaction from NASA, the institution we entrust to monitor the heavens for existential threats? So far, a deafening public silence. Much like the scenario in which OpenAI refused to comment on its defiant AI, the lack of a prominent, clarifying statement from NASA is unsettling. While news of the Kaib and Raymond study has been reported by various science journalism outlets, there has been no major press conference, no agency-wide memo to the public addressing the findings. What could this silence mean? Is it because the timescale millions or billions of years is so vast that it doesn't register as a present-day crisis worthy of a major public announcement? This is a dangerous path to tread, as it fosters complacency toward long-term risks. Or is it possible that NASA is downplaying the findings to avert public panic, choosing to quietly incorporate the new data into their own long-term models without fanfare? Perhaps, more cynically, in an era of tight budgets, an unaddressable threat that won't manifest for eons is a problem that's easy to put on the back burner. Whatever the reason, the lack of a clear, transparent response only fuels anxiety. When science points to a potential failure of our planet's most critical safety system, its stable orbit, the world deserves to hear from the experts on the front lines. Their silence leaves the public to fill in the blanks, and the imagination, fueled by such terrifying possibilities, tends to paint the bleakest pictures. So what's really going on with the physics here? The thing is, this isn't some new mysterious force. We are seeing the well-understood, but deeply unsettling, consequences of gravity, governed by a classic puzzle in physics, the three-body problem. In the 17th century, Isaac Newton laid out his laws of universal gravitation. For a simple two-body system, like a single planet orbiting a single star, the equations are elegant, solvable, and predictable. Their orbits are perfect, stable ellipses that will continue forever. But as soon as you add a third body, say, another planet, or, in this case, a passing star, the system's behavior becomes fundamentally unpredictable over long periods. There is no simple general equation that can describe the outcome. This is the essence of the three-body problem, and its modern incarnation is chaos theory. The solar system is not a two- or three-body problem. It's a multi-body problem of staggering complexity. The stability we enjoy is a delicate temporary truce in a chaotic system. A passing star acts as a powerful agent of that chaos. It doesn't need to break the laws of physics. It simply needs to exploit them. By introducing its own gravitational influence, it breaks the fragile truce, reminding the planets of their inherent potential for unpredictable behavior. The other key concept is resonance, the same principle that allows you to push a child on a swing higher and higher with small, precisely timed shoves. A tiny, repeated gravitational nudge from one planet on another, if it happens at the right frequency, can amplify over millions of years, turning a stable, nearly circular orbit into a wild, eccentric one that crosses the paths of other planets. A passing star can initiate new, destructive resonances, or amplify existing ones, pushing the entire system past its tipping point. And just when you think it can't get any worse, you find out it does. You see, As if the threat of a rogue star weren't enough to occupy our nightmares, a separate study warns of another, closer danger hiding in the blinding glare of our own sun right next door. Research from astronomers at São Paulo University in Brazil, currently under review for the journal Astronomy and Astrophysics, has turned its attention to Venus. Their work suggests that our sister planet may be shepherding a swarm of currently undetected co-orbital asteroid space rocks that share Venus's orbit around the Sun. Here's the terrifying twist. The very co-orbital status that protects these asteroids from crashing into Venus does not protect them from encountering Earth. Their orbits, while gravitationally tethered to Venus, are not perfectly stable and can evolve over time to cross the path of Earth. We could be blindsided by an asteroid coming from a direction we rarely monitor with such intensity. The researchers explicitly state their goal is to assess the possible threat that the yet undetected population of Venus co-orbiters may pose to Earth. The problem is one of detection. Because these asteroids orbit closer to the Sun than we do, they are almost always lost in the Sun's glare, making them incredibly difficult for Earth-based telescopes to spot. It is a hidden threat, a fleet of potential planet killers orbiting just one planetary door down. This revelation serves as a humbling reminder that cosmic dangers are not just distant and theoretical. They can also be close, unseen, and lurking where we least expect them. What really brings up a lot of questions is what this all means for us. This confluence of research rips the lid off the Pandora's box of cosmic fatalism. It forces us to confront the profound fragility of our existence. For all our progress, for all our technology and ambition, we are fundamentally at the mercy of celestial mechanics. We live in a universe that is not inherently safe or designed for our benefit. We are simply the winners so far of a great cosmic lottery. This is humanity's ultimate control problem. With a threat like rogue AI, the problem is one of controlling our own creation. We can, in theory, build better safeguards, program better alignment, or choose to pause development. But how do you solve the control problem for the universe? How do you install a safety protocol on gravity itself? How do you tell a passing star to please keep its distance? This brings us face to face with the unnerving possibilities of the Fermi paradox, the question of why, in a universe so vast, we have yet to find evidence of other intelligent life. Perhaps the answer is that the universe is simply too dangerous. Maybe intelligent civilizations arise from time to time, but they are inevitably snuffed out by random cosmic events like a stellar flyby, a gamma-ray burst, or a major asteroid impact long before they can spread across the galaxy. This research shows us just how easily a planetary system, even one that has been stable for billions of years, can be violently undone. Our continued existence may be less a testament to our resilience and more a reflection of a temporary lucky streak. So faced with this, the instinct is to ask, can we fight back? The thing is, the answer is deeply sobering. Our current planetary defense initiatives are heroic and technologically brilliant, but they are designed to solve a much smaller problem. NASA's Double Asteroid Redirection Test mission, which successfully altered the orbit of a small asteroid in 2022, was a monumental proof of concept. It showed that we can, with enough warning, nudge a dangerous space rock off a collision course with Earth. We are developing better telescopes and survey programs, like the upcoming NEO surveyor, to find these threatening asteroids. But these tools are like bringing a slingshot to a battle against the god. The DART mission slammed a half-ton spacecraft into an asteroid. How do you counter the gravitational pull of a passing star that has the mass of our own sun or more? How do you build a spacecraft that can correct the orbit of the Earth itself, a planet weighing 6 sextillion tons? The energy requirements are so far beyond our current capabilities as to be indistinguishable from magic. We cannot build a planetary shield. We cannot lasso Mars to stop it from hitting us. We cannot put the brakes on a planet that has been gravitationally shoved toward the sun. It's really strange, but given everything we now know, where do we go from here? This knowledge is now out in the world, amplified by science media. Will it serve as a galvanizing wake-up call? Or will it be dismissed as morbid curiosa, a problem for a future so distant it feels imaginary? The muted reaction so far suggests a dangerous complacency. If this research had found a 0.2% chance of a global economic collapse next year, there would be emergency summits, frantic market reactions, and non-stop media coverage. But because the timescale is in the millions and billions of years, it triggers a cognitive bias that allows us to dismiss it. It's the same psychological hurdle that complicates action on slower-moving crises like climate change or biodiversity loss. One rogue star and everything we know could be gone. The universe doesn't owe us safety. So the question is clear: will we wait for chaos or take control of our destiny? Let us know in the comments, smash that like, and subscribe for more.